Good afternoon. How's everyone doing? Who's all here in the chat? Because we've got some 201 work. We got some 320 work. We got some 474. Who's all here? I don't know if anyone's here yet. Say hey if you're here in the chat. We might do some My Pearson. What do we have? Let's see, I'm getting us some stuff loaded up right here. Hey, Blake. Hey, Aaron. Good to see everybody here. What questions do you have? We'll throw out some points right here. What are you working on? Mubot should be awake. Mubot is there in the chat. Do you not see Mubot? He said hey to Aaron. He didn't say hi to you? Mubot, what are you doing? Mubot, you stop doing that. Mubot, sorry right there. Mubot's gotta up his game. Gotta do better. Gotta get your head in the game. What should we work on? You name it. We'll work on it. Chapter 5 is gonna be the big one. How are people doing on that? I'm gonna go look at grades here real quick on that. Because chapter 5 is no joke. And starting it the night it's due. Don't worry if you're hearing this right now and you're about to start it. How many incompletes are there? Oh my gosh. 2/3 of the class has not started it yet. 2/3. And it's due tonight. Chapter 5 is a tougher chapter. Can we give out... We just give it out as we work through. We give it out as we work through. So what should we do? What questions should we do? We might need to do some chapter 5. Was last class close to 70K? Oh my gosh, I gotta slow down then. You have to be here though. You have to be chatting. You have to be chatting. We have sometimes. You want to do chapter 6? Question 4B, first question of the day right here. 4B for homework 474. Not sure what to write for all these responses. Let's go look at that. So remember, if you're here, drop those questions in the chat. Okay, question 4B. Do I have the homework open? I do have the homework open. Okay. BAS 474. Homework 4. Question 4B. Or not 4B. Question 4B. Let's go take a look at that right here. And it is at 5:03. Here we go. Let's go check it out. Okay, Sam, good to see you here. We've got some clustering, and let's look at what 4B wants us to do. 4B is with some k-means, it looks like. So k-means is when we're trying to figure out how many cluster centers there are via unsupervised learning, meaning there is no answer to the amount of clusters we have. Dendrograms are similar. We got a dendrogram here from class that we just made, which actually has probably about 4 clusters, but this is just one dendrogram we could make. There's many other ways to make the dendrograms. There's some elbow plots from us running the k-means, and here's a dendrogram, different answers for different questions. And it looks like 4B says right here, Kroger is interested in using the cluster identities to aid in identifying segments where customized offers could be designed. Example, people who cook, people with pets, people with babies. While the clustering scheme you've just found is valid from a technical and algorithmic viewpoint, the end result is not very interesting and definitely not useful to Kroger's application. Determine how many cluster differs from each other. Determine how the clusters differ from each other. Then explain why Kroger would not be interested in this cluster scheme. This is by far the most important question on the homework. Okay. So what you want to do, and I don't think we have our data up here anymore. We don't. When you run hierarchical clustering or k-means, you will end off, and we could run our data probably here. This stuff we did from class. Did we get it? There's the elbow plot. Ooh. But that's the, did it? Iris copy? Ooh. So that's k-means 2. Ooh. So let's go over here and run k-means on the iris copy. Let's run k-means 2. And let's go to iter max equals 25. And start equals 50. There it is right there. let's store it as output so we can work with it a little bit easier. Does this make sense what I'm doing right here, Sam? I'm creating the k-means algorithm, kind of doing similar to what you're doing, and I've got cluster IDs now. These cluster IDs are going to be important. I'm going to store them as IDs right here so I can save the IDs. I'm going to go back to the original data frame and store the IDs on the original data frame as IDs. So now I've appended onto this cluster IDs. Now, this is where you want to get to because, and so when we're interpreting it, we might want to look at the z-scores or we might want to look at the original data. So you, as someone who knows what z-scores are, might go here and go to aggregate, and we would aggregate all the y variables of interest by the cluster IDs. That's y tilde x right there. Then we'd say data, and if we want to look at the z-scores, I have that scored into iris copy right here, and fun equals median, so we don't have things that are going to be heavily influenced by outliers. So if we take a look at our groups right here, we see the median petal length. Well, they're both, ooh, that's interesting. If we do mean, we'll see, ooh, why are all the z-scores above average? Oh, because skewed data maybe? Interesting, that's weird. Huh. I don't even know how this is possible. These should be z-scores. Let me look. Supple length. I'm going to go to the copy. Oh, we didn't scale the data. They're not z-scores. Why is our data not scaled? Oh, I know why. Because we don't have the functions. Since I reloaded my global environment, we need to go back to the lab. And when I ran the scale data frame, it didn't do it. Because I was thinking z-scores, they shouldn't both be positive. So we're just going to rerun this real quick again so we can actually get the z-scores. So now when I do the scale data frame on this, we are actually going to have a scale data frame here. And this is actually going to probably make a different elbow plot now. So let's make the elbow plot. And it's still about 2-ish. But let's run the algorithm here. Let's store our cluster IDs again, overwrite the cluster IDs, and now aggregate. And now we see z-scores that look more like they should. So those z-scores, you shouldn't have all positive z-scores. Z-scores is where the mean is at 0. So this is chapter 5 review for 201. So I was like, theoretically, those z-scores don't make sense because they can't all be positive because there has to be a mean to the data. And the mean, like if something is at the mean, it would have a z-score of 0. Everything can't be above the mean. That's just theoretically impossible because the mean's the average. So there has to be something below the mean or everything would be on the mean. So we see now this is below the mean, below the mean, below the mean. So these are kind of only bigger in the supple width. So your important thing to do right here when you look at your data is to think, how does this matter? Well, supple, what is the supple of a flower? Supple width. I know what the petals are. The supple is at the bottom of the flower. So these are very short in their petals, very short. So these are like nice little cute flowers, I'd say, where the flowers in group 2 have a longer supple width and they have longer petals. These are like your big flowers, like your big blooming flowers. So maybe you're looking for little cute flowers, you go for flowers in 1, where flowers that down here are going to be your bigger flowers. So this might be important to a florist if you think about it right here, because we really have like big versus small flowers, if you ask me. It's interesting to me, though, that the supple width doesn't follow the pattern. For the smaller flowers, they actually have a wider supple. So interesting right there, but that's actually less of the differences right there. You notice right here, the absolute distance right here is a distance of about 2, where the absolute distance here is of a distance about 1.2. The distance here is about 1.5. So this is the smaller difference category right here. And if you notice, they're both smaller z-scores. So you have to think about what this means to the actual group you're talking to. You probably want to go in now and take your data and look at it on the original data. So we've got the IDs. I think I stored them to the original. There's the IDs, and we put the IDs right over there. So let's go to the original iris data and look at the means here. So if you look at the means on the original iris data, we won't worry about species because that's just doing a categorical variable as quantitative. You can see right here, there are some pretty drastic difference on petal lengths, especially. So the petal length is how long the petals are. So we really have some much bigger flowers in flower group 2 as we thought. And the supple length is not as distinctive differences. So it's really some big, if you ask me, it's the big, I'd say extravagant flowers in group 2. So you want to think about what this means. Does that make sense, Sam? Like, I don't want to interpret your data, but this is what you're going to be showing to the company. and saying your group 2 customers are this. Hey, so many, good to see you here. Doing well. And so you want to think about, what does this mean? What does group 2 mean? You probably want to look at the z-scores to begin with and say like, okay, this is way below average. Like this is a pretty good bit below average for both of these. And you can see it right here in the actual data. And then over here, you have above average, below average, above average, above average. These are really just your much smaller flowers, it looks like. The supple length, or supple width, excuse me. But Sam, what are you thinking? I don't want to work the exact problem, but this is what you're doing, is you're aggregating the data and then talking about it to the consumer and saying like, here's the groups we have. Group 1 is best described by this. And think about this, what they want is look at the wants and the needs of the consumer, of the company. Kroger is interested in using the cluster identities to aid in identifying segments where a customized offer could be designed, like people who cook, people who do this, people with pets. So they want something where there's distinct like standouts. So take a look at your data, and Kroger wants to be like, these are our cooking customers. These are our pet customers. So you want to look at your clusters and think if it meets that sort of clustering scheme that they want, where they could say, these are the people who cook, these are the people who have pets. Does that make sense, Sam? Again, it's more direct to the problem you're working on. So think about, they want the clustering scheme to show like, this is my cooking cluster, this is my this. Yeah, so you get where I'm going with that, Sam, right? If you look at it and be like, okay, so what do these numbers mean? Because this is just output right here. Then we have to talk about and interpret what it is. Well, yeah, well, we're going to like, you have to look at this cluster and say, what defines this cluster? And this cluster over here is defined by smaller flowers. The negative z-scores on it, it's mostly smaller except for the supple width being bigger. So these are your smaller flowers and these are your bigger flowers. That's how I would talk about those clusters. Like if I had to give them names, I would say typically smaller flowers, typically bigger flowers, where they have much bigger petal lengths. Like the petal length is the bigger characteristic, but in general, they're just bigger flowers. These are your smaller flowers. So you have smaller flowers and bigger flowers. Yeah. And just try to write a good bit and make sure it's quite clear you understand what the output's showing you, because Kroger's like, okay, so we want cooking customers, we want pet customers, we want the clustering scheme to find out these customers who generally are buying this and customers who are generally buying this. So that way we can send them kind of like targeted coupons to be like, come in for a pet day and get this % off. And you're like, oh, I've got a bunch of pets, I'd love to come in for that. So they are trying to create the segments in their population that put customers into like a defined cooking group, a defined this group. So they're really looking for standouts with z-scores, or so I'd look at the z-scores first. Then you could look at the original data. But z-scores is going to be what we look at as people who analyze data, because z-scores fairly compare everything. Because what are big differences down here? Like you might go, oh, that's a big difference. Well, actually, it kind of is. But you want to use the z-scores to get the best sense for what's going on. What other questions do we have? We got one question down. What else do we have? You tell me. What other questions do we have? It is open floor. Blake, did you say you wanted to do some question 2 on 474? On which one, Aaron? Question 2 is at 474? Question 2, 474? Do we have visualization assignment? Is it coming up? We might have a visualization coming up. Question number 2. Let's take a look at question number 2. 474, question number 2. Ooh. Here we go. We can take a look if we have a visualization. Okay, with question number 2 right here. In the global environment, you will find a function called scale data frame. Yep. Do we not? Oh, because you load this. That loads the scale data frame. I was like, I loaded up the activity data to get it. So that loads the scale data frame right there. And we've got the Kroger right here and all this good stuff. Now, an important thing to know is like, why would we do Kroger plus 1? And you have to take a look at the Kroger data to understand the reasoning for that. Here's the original Kroger data. And why would we add 0.01 to it? So I'm trying to show you something right here. We're about to log tenant. And why would we add 0.01 to it? I guess that's fine. Why would we add 0.01 to it? Log 10 of Log 10 of, it's not 1. Good answer, Sam. It's not 1. 100 points right there. It's not 1. Log 10 of 0 is not 1. Very close. And then Chase has it right there. Exactly, Chase. It will say negative infinity. Log 10 of 0, which are some of the values. Like if you try to log 10 those values, you get negative infinity, which then if you try to plot that, like if we do a histogram of Kroger and we go alcohol, here's the histogram of it like this. And now if we go here and do a log 10 of it, it's probably going to get really mad at me because of the negative infinities. Oh, it worked? It worked? It might have just excluded those data points. So I don't think it's actually showing those. Let's add the +1 to it. The plus log 10 plus 0.01. There we go. Yeah, so it actually just totally excluded those values. So that would be a big problem right there because it's not even using those values. It's eliminating those values. Now you notice there's a huge spike right there. It's probably going to look the exact same if I add 1 to it. Let me check out because I'd preferably add 1. Yeah, just preference on how you do it. When you log 10.01, it becomes -2. It's how many zeros there are. So when you do these smaller numbers with log 10, you count the zeros and you get -2 because 2 zeros backwards. Like log 10 of 100 is 2, so log 10 of 100, you just count the zeros and it's 2. So log 10ing is going to take away extreme values and put them all on an even playing field. So we do this to kind of make the data more normal. Take a look at the original data. The original data is very skewed, and then when you log 10 with the +01, you get a much more normal shape. You do get this weirdness down here. I mean, that's about as normal can get, but you do have the outliers down here who are buying nothing. It's weird. It's like you're an outlier if you do not buy it, which I guess that kind of makes sense. If you look through the customers, there's a lot that buy nothing, right? There we go. Now we got some people who bought like a 1 beer. So there we go. Interesting how data works. Left arrow, the result of running the scale data frame into Kroger scaled. So make sure to run this function right here. It'll actually run if you highlight it, I believe. Yes, it does. And then store that into Kroger scaled. This will add a penny to each value. That way we can take the log 10 and we don't get things like negative infinity. And then we're going to scale it. So it's on a 0 to 1 scale right here. So you can see it right here. This has not been scaled yet because if you did scale it, you would see that the center of the distribution would be at 0, and it's not. The center's down here somewhere, like currently, or this, excuse me. The center is here, but 0 is not the center. Run, apply, and then this is just to check what? Why would we run this right here? Because this is going to tell us the mean. Don't change what I'm changing. This is going to tell us the mean for everything. If you scale your data, the mean for everything should be what? If you turn everything into z-scores, the mean would be what? If you turn everything into z-scores, the mean will be what? If you turn everything into z-scores, the mean will be what? Like if I said mean of scale empty cars of this vector, if I scale this, the mean of it will be what? By scaling the data frame, so don't delete what I deleted there. Don't delete what I deleted. Should be 0. Boom. Now, that doesn't look like 0, does it? That's the thing you're going to be like, wait, that's not 0, Brian. Can anyone type that in the chat for 1,000 points, what that number is? Because you need to know what that number is, and it's just some change being carried around in the background. So I've had people be like, that's not 0, and I'm like, well, it's basically. What is that number? 1,000 points if you know what that number is. Who knows what that number is? What is that number? What is that number? Yeah, it is scientific. Great job, Aaron, right there. Yeah, exactly. Darren, get it? Aaron, you might be right. Oh, and then, I didn't grab the point. I was like, what? Nice job, Aaron. 1 extra 0. Don't worry, we don't have to. You can actually do it like by typing like 2e to the -5, and it'll do it for you. Like, you can see it if you do that. It'll do, remember to count the leading 0. Sometimes I forget, but it'll do it for us. The biggest thing to know, like, you have to know that that is a very small number. Then writing it out, we usually don't have to do. It's just a very, very tiny number. It's because when R does calculations, there's sometimes like little things that just don't work out. So it's literally the idea of R carrying your decimals to like the 22nd number after the 0, and there being something that didn't work out perfectly when it did it. So R is being too good at what it does. Now, when you do when you scale data, what should be the mean? What should be the standard deviation of your data? When you scale data, what should be the standard deviation? These are really good 201 questions. We're turning them into z-scores. So what should be the standard deviation if we scale data? What should be the standard deviation? So I'm scaling this vector inside a data frame right now. I'm not doing the exact same thing right here, which applies the standard deviation function to the Kroger data frame to all the columns in it. 2 stands for columns. So apply the standard deviation function to all the columns in the Kroger scaled data frame. If you get the standard deviation of scaled data, it should be what? If it's working, you will get this. All your standard deviations for scaled data should be what? If data has been scaled, all the standard deviations should be what? There's z-scores. So when you have a z-score, boom, Chase, you got it right there. Yep. A lot of this, and this is why I try to tell 201, I'm like, everything we do builds. Great job, Aaron, right there also. More points in the chat. Everything we do builds because we are doing this in 201 currently. They have homework on it tonight because they're just using z-scores right here in 201. And then what's amazing is if we want to find z-scores in 474, I can just find you all the z-scores like for this data. Here's my data empty cars. And then I can find you all the z-scores of it by doing that. And I could store all the z-scores here by going to z. And there's all my z-scores. That's every single z-score for all the data right there. I could make a histogram of my z-scores and show that they have a mean of 0 and a standard deviation of 1. Mean of my z-scores is basically 0. Standard deviation of my z-scores is going to be 1. There you go right there. Have you gone over the for loop in question 5 yet? We could do that. We could do that next year. It's a lot of 474 today, but yeah, keep asking those questions. You just ask the questions, we do it. Yeah, so I think this is good. Did that do everything right here? This is just the data preparation. I didn't write the code, but we explained what's going on and it should make sense. Does that make sense, Aaron? How are you doing on that? We're going to probably do question number 5 next. But who's ever here, ask the questions. We do the questions that are asked. So you ask the questions, we do the questions. And we're on open questions right now. So if you're 201, if you're watching this, just drop a question in the chat. I know you got an assignment tonight. Okay. You're welcome, Aaron. Great work. We're going to go to question 5 now. Okay, this is the fractions one. I think I did this in a previous office hours, but we can do it here too. Okay, so they're interested in the fraction. So whenever we write a for loop, what do we first write? Whenever we write a for loop, we first write a this. I've helped a lot of people on Discord on this one too. There's been a big ask on Discord. Whenever we write a for loop, we write a what? That skeleton, you know it, you love it. He's right over there. We write a skeleton to begin with. So when you think about this, we're taking the fraction of each row. I think, are we deleting out some rows? We delete out the rows afterwards, yeah, because of redundancy in the data. So when you're doing this, you want the fraction of what customers spent from the original Kroger data set. So you want to do it for one row first. How can I get the first row? Great job, Javen. We might make an empty vector. How can we get one row first? How can I get the first row of the Kroger data frame? How can I get the first row of the Kroger data frame? That's all I want to do first. I just want to, and then look at the fractions of what they spent. Like if Brian spends most of his money at Kroger, close, Chase, super close, Chase. We won't use the Kroger scaled because that's scaled. We won't use Kroger scaled. And then, so we use Kroger, but Kroger is a data frame. So Kroger is a data frame. So what should we do at the end of it? Remember, Kroger's a data frame. Rows, columns, rows, columns. So Kroger's a data frame. Great job, Javen, right there. More points in the chat. Yep. We want to do rows, columns. So this is the first row. The first thing we put in is the rows we want. The next thing we put in is the columns. And so we want to put that in. Don't worry, I've made that mistake many times. So that is the first row right there. How could I find out how much that person spent? How could I find out how much that person spent? This is, they spent $42 on pet, $219 on other, $254 on meat. How could I find out how much they spent? Just do sum. There we go. And then why not take that and do vector mathematics and there's their fractions. So now we've found the fraction that that individual spent because we're just taking each amount they spent and dividing by the total. Does that make sense theoretically right there? It's like, okay, you spent on alcohol, you spent $43, and we're going to divide that by the 3,000. So that's why it's about 1.4% because $30 would be 1%, extra 15 is an extra 0.5%. So 43, you could literally just take and check if you want it. It's just doing this for you for all the values. And there's that value right there that you see. Right there, rather. So when you're doing this, good to see you, Blake. It's just going to find for you the fraction for each one of them. But when you think about this is where I kind of give you like tips here from here. We want to do this for every row, right? So when you're doing this, you could just plug in here I, and you could run it for this. Now you want to store this. Hint, I had some people working this and didn't store it. But you could run this for the first row. You probably want to store the output into some sort of fractions data frame. And then you could run it for the second, run it for the third, and you'd want to run this for how many things? How many times would you want to run this code right here? Because I've shown right here by doing this that I've created a skeleton. He's just super excited all the time for the skeleton. But with this, we'd want to run this for how many things? I wouldn't use length. Pretty sure. Length is good answer right there, but length is going to get you how many columns there are. So the number of columns is actually the same as the length. So length is kind of, you might think it's length, but no, like Grant, so let me throw some points for that. You wouldn't use length because length is the number of columns. The number of rows, exactly. So you'd want to do it for the number of rows right here, which the number of rows of Kroger is going to be how many rows there are. That's for each individual customer. Because you want to know what you're working with. You have a list of customers right here, and you have how much they spent. Like this is customer 1's spending on alcohol, customer 4's spending on alcohol. And you have the different categories of what they bought, and you're looking at what did they spend. So it's very important right there to make sure you understand the data you're looking at and being like, I have to do this for all my customers. Each customer's in a row, so I need to do it through all the rows. And then we need to store this output. So when you think about this, we have a lot of what we need right here to write our for loop, where we already have our placeholder variable. We know what we need to go through, make sure to do 1 through it, and then we need to store this output into a row in the fractions data frame. So let me repeat that one more time because that is basically the answer if you know how to write it. We need to use our placeholder variable. We need to then go 1 through the number of rows. And then we need to use our skeleton, but store the output of our skeleton into our fractions data frame, which is something we should create probably before we do this. So make sure to create the fractions data frame. So that's a lot of really good help for this right here. A lot of components. Is that making sense, Chase? So we can do more questions. Drop those questions. I try to like give you a start to it, talk you through it a little bit here, show some advice for it. Not do the full thing though, but just like talk through the advice of it. So do I need to store? You don't have to. This is not required. Yep. This is just the practice work right here. Like I would even comment, like, you don't want to write down all this stuff I'm writing down because it's just extra nonsense. Like never write down everything Brian writes. Never write everything Brian writes. You want really just to have the for loop here. And you want to be careful because sometimes I've had people like write down everything I write and then it creates excessive output. Like if I were to put here Kroger to view, don't even know how to spell Kroger, but if I were to put Kroger to view the Kroger data frame and you were to knit this file, this would create excessive output. So let me delete that because I really don't want someone to put that and lose all their points. For question 1, can you talk through the skeleton? For the first question on the assignment, we can do that here, Javen. Thank you so much, Javen. Let's go put that here. We need a for loop. Let's go check out question 1 on a for loop. 3103. Let's go check that out. Question 1. It's right. Here we go. Include a histogram of the values of cooking. So we want to make a histogram over here. Classic hist will do. Worked on so far. We've been working on a lot of 474. Kenneth dropped some 201 questions in the chat. Good to see you, Kenneth. So by using apply or by writing a for loop, print to the screen the max of each column. So the reason we're doing this right here is we're trying to figure out the range of the values, which really goes to we need to be scaling our data because there's going to be some extreme values. So print the max of each column and print the screen the min of each column. There are reasons that design a clustering scheme based on the recorded values is a bad idea. identify them. So what's really great right here is the apply function. What apply does, so if you watch what I do right here, I'm going to explain how the apply function works, and I hope you can figure out how to write what I'm about to do with the apply function. Apply function is amazing. We love it. The apply function, absolutely amazing. Awesome function. So what apply does is, if you say apply, and then, for once I don't like the snippet. When you say apply, and you take something like the empty cars data frame, if you enter in 1, it'll apply whatever you say to the rows. If you enter in 2, it'll apply whatever you say to the columns. So let's look right here. 1 applies to rows. Oops. And 2 applies to columns. So think about this. This is going to find the standard deviation of all the rows. This is going to find the standard deviations of all the columns. Notice how the columns are the names of the what in the data set. The columns are the names of the what's in the data set. Remember how I said if you put a 2 right there? The columns, because this is now the standard deviation, because remember it's the columns, 2 applies to the columns, 1 applies to the rows. This has what are called row names to it. So this is the standard deviation of the first car right here. The variation in the data within it. We could find the mean for the first car. And there it is. We could actually just get the first car if we wanted. So there's the mean of the first car right there. We can look at the mean for each of the cars for all their variables. Probably wouldn't make sense. We could look at the mean for all the variables. There's the mean miles per gallon, the mean cylinders. We can do things like the range of values for the first car. There's the range of values. We can do the range of values for all the variables. And there's the range of values for MP cars. You could find the max and the min individually, but that finds everything. So there's the min right there, the min of all the variables. Here's the min value for each of the cars. A lot of zeros. But yeah, so Javen, you see it right there. But if you notice what's going on, you can either do it for all the rows in the data frame or all the columns. So the 1 or the 2 says, 1 says you're doing it for the rows, finding the min of the rows. A 2 says you're finding the min of the columns. It just switches the way it uses the function to either apply what you say. So it applies that function to either all the rows or applies it to all the columns. And it's super powerful because you can just get the standard deviation of all the cars or the standard deviation of all the variables, just like that. The way this data frame looks is each row is a car in the data frame telling us different characteristics. So when I do apply and then 1, I found the standard deviation, the variation within each car for all the variables. Not really that good, though, because everything's on a different scale. Now, much more applicable would be the standard deviation of like miles per gallon, which you see miles per gallon has more variation in it than the cylinders of a car, as we would expect. Cylinders doesn't have a big range of values. And you can just use range to get range. So, I mean, a lot of really quick, nice functions, and that's why when we code, it just makes life easier. Kenneth, which one were you wondering about? I think we're doing great. We've just been destroying some 474. We've already done 4 of the questions, and I hope people are understanding. Let me know if you have questions. But we've already done 4 of the questions. We've done like a third or half the homework, just talking about them, explaining how to do them. What other questions are there? We might do some 201 if no one says anything. Medical researchers followed, Blake. Good question there. This is chapter 6, right, Blake? Chapter 6. Oh, I have put down 51. I was like, what happened? Did I warp through time? Chapter 6, right? Chapter 6? Nice. Let's hear with the base screen. Stat 201. Chapter 6, quiz. Medical researchers followed a bunch of men around. Like, isn't it, I'm making a histogram on jump, but the bin size is just the size of each value, so it's a straight line. It, which are you working on a particular question, Kenneth? Which one are you working on, Kenneth? Is it a particular question? Or are you doing it for your own work? Because it's even cooler if you're doing it for your own, like you're doing like a project or something. Alpine Men Downhill. Okay, and that's one of the ones on chapter 5, right? We can do that one here next. Is it chapter 5 quiz part 2? Here, we'll do that next. You got it, Kenneth. Let's do that next, and then I'll make sure it's working. Oh, I think I know what you did. Is the variable red or blue? When you look over, no worries. When you look over to the right, is the variable red or blue? I bet I might be able to fix the problem here. I bet it's red, right? Is it red? I'm finding, we can do this one next. The variable's probably red, right? And so your distribution looks very flat, right? Is it red? Once you confirm it's red, then I know it. It's red when I click. Well, no, like on the far left of the screen, it shows you the thing of it. Hey, Katie, good to see you here. Yeah, we were doing some forcing for a moment ago. Drop another question. We'll do it. So, Kenneth, what I want you to do is I want you to go to File, New Worksheet. File, New Worksheet. Edit, paste with column names. File, New Worksheet. Edit, paste with column names. I'll repeat that again right here. File, New Worksheet. You're welcome, Katie. Excellent work. File, New Workbook or New Worksheet, the top one, New Data Sheet. Paste with column names, and then it'll be blue, which means it's quantitative, and then try it right there. I think that'll fix the issue because it brought it in as categorical, and then it was treating it as a categorical variable, so it thought you wanted categories because the column name went into the first row, and it thought it was words. Here we go with the question. Let's do it. We can do that one here next, Kenneth, and tell me if that fixes your problem. We're going to do this one, and here we are with some chapter 6. You're welcome, Kenneth. Excellent work. Medical researchers followed 1,435 middle-aged men for a period of 5 years, measuring the baldness. Oh, no. No. Is that right? Right there. There we go. I don't know. Ah! It doesn't matter. Thank you, Rock. They found a correlation right here of 0.089 between the two variables. Comment on the conclusion that this shows baldness is not possible cause of heart disease. This is like the happiest question in the world. Baldness and heart disease. Oh my gosh. Well, it's interesting. This is very interesting. Comment on the conclusion that shows that baldness is not a possible cause of heart disease. Even though it's represented as numbers, this is categorical data and not suitable for correlation. Yeah, and they're kind of doing ordinal data right here. This is quantitative. But correlation does not imply causation. This is such a weird question. Like, you can mathematically calculate it with what they did right here. They did binary operators. They're kind of doing like a logistic. It is. I'd love to talk to the person who wrote this question because this is a pretty ridiculous one. It's really, even though it's represented as numbers, that's a good way to say it. Even though it's represented as numbers, this is categorical data. That is a fact. Like, even though it's represented as numbers, this is categorical data. Yeah, because the distances between the ordinal groups is not that well described. So yeah, it's the distance between the ordinal groups is probably the big issue. Yeah, that's a weird one. It's the weirdest one I've seen in a long time. Because the first condition of correlation is QQ straight enough, no outliers. And so it's like the proper way to analyze this would be with a mosaic plot, because it is, when we look at the baldness and the rate of heart disease, it would be a mosaic plot. Yeah, no, totally. Yeah, no, this is no big, like our favorite, right? This is an okay question. It's just that, like, I agree with them. You can mechanically calculate it, but really this is something where we're representing categories with numbers. The one issue I had is this is kind of ordinal up here. Ordinal means it goes in order of like none, little, some, much, and extreme. So if the other variable, which is almost like a Likert scale, if anyone's ever heard Likert, Likert, if anyone's ever heard Likert scale, this is almost similar, like strongly disagree to strongly agree. You could almost look at the correlation, but the thing about Likert scales is they're perfectly spaced apart, where you have like strongly disagree, neutral, strongly agree. Something like that is going to be more of like actual spacing, and then you could quantify like on a 1 to 5 or -2 to 2. Sometimes we like to put 0 at the center of it and then go -2 to 2, and then you could quantify people's correlation with questions. So it gets into a little bit of like advanced statistical ideas of sometimes an ordinal variable, because literally we were talking about this in 474, so Katie knows we sometimes have to deal with an ordinal variable as a quantitative variable. So if a variable is ordinal, then there might be meaningful quantitative values we can assign to them. So that's where I was starting to think. I was like, and then it's a binary operator of somebody being bald or not bald. I mean, someone having heart disease or not having heart disease. So that's where I started to like overthink it and go to upper level classes where we talk about, we can convert things because some of our algorithms that we use require us to convert them to be quantitative. So I was like, where are they going with this? We could go advanced with this. Okay, so I did a new sheet and then paste the column, but it's still red on the left. Let's do that right here, Kenneth. Let's do Kenneth's question on the alpine downhill. And Chase, you bet. Let's do that here, Chase, after this. Thank you, Chase, right here. Let's click this button. Okay, got some hype music here. Oh, nice job. Katie, 1,000 points helping Chase out right there. That's the kind of advice we love right there, saying like, do this, do this. It's what we love in the chat. So here we go. Will it be that? No, we don't like vague stuff. There's every once in a while a question on my Pearson that's kind of like, I wouldn't word it that way. We are doing Stat 201, Chapter 5 quiz, Part 2. Hype, says Kenneth in the chat. I need to play more of like we got a whole bunch of songs on here that I never play. I need to look at the YouTube library again. This song's like almost like experimental jazz, it sounds like to me. It's got a lot of like off beats and stuff, or like things that are like appearing randomly. Alpine downhill upcoming. Yeah, that's what I think it's why I took it. It sounds like you start the battle, right? Wait for it. It does sound like you get an encounter and then it goes. That's exact, like it sounds like Final Fantasy VII, like an encounter starts, like the screen swirls. Here, wait. I got something special for you. Alright. Hopefully I picked the right one. Wait for it. When we start this question. You ready? Just wait for it. You're playing through 7 right now, the original with Cloud and Sephiroth. The original one. Because they do some re-releases. They're like doing the new 7 whatever. I don't know. I need to get those. But I'm playing Elden Ring. Last night I stayed up a little bit and played some Elden Ring. If Brian's ever tired, you'd be like, Brian, where'd you get to in Elden Ring last night? I'd be like, oh, you don't want to know. You don't want to know. The original, are you excited for the new remake part 2? Yeah, I know, right? It is part 2, right? The alpine downhill skiing thing. It is oh, here it is. I found it. 53 men completed the alpine downhill. Awesome. 2 seconds right here. There it is. And let's timestamp this. And here, Kenneth, this is for you right here. Let's do this. Okay, there we go. A little special transition between screens right there. So let's take a look at some alpine men skiing right here. Oh, Amanda asked, do you game in your class streaming room? I've thought about it. I need to ask UT if they'd let me do a gaming stream or two. I'd love to do some Binding of Isaac. What's my favorite game? They'll play that game. Elden Ring and Binding of Isaac are what we're playing right now. And some Mario Kart, of course. Some days I get to game, some days I get to not game. Last night I got to game a little bit. You'd watch Kenneth. Awesome. Maybe if UT says, hey, you can stream some game. Do you have decorations in your office? Not too many. Got Mega Man. Got some drawings from my wife. So got some stuff, not too much, but we should do some more when we get to the house in Knoxville. Gonna be tons. Like physical space, not the virtual one. Do you play game in your class streaming room? I'll clarify. Does Morty accompany you? He should. He should. Oh, he'll come to Knoxville, of course, of course. Morty and John, of course, of course. We love our bunnies so much. Okay, here we go. Let me read timestamp real quick. Okay, 47:03. Here we go. I like the room you're in right now. Do you play video games? Oh no. This is just the office. It's got a desk for Chelsea, a desk for me in here. So it's a pretty small room. I can show it here afterwards. But no, the main room is where all the gaming happens. Even though there's like a gaming PC kind of. So we have right here the data. And this is all quantitative data. So here you go, Kenneth. Check this out. Oh, we can do some number 3. You bet. You bet, Kyle. Copy to clipboard. And now I need to reopen my jump license. I need to get my jump fixed. Every time I open jump these days, it's like, please input your license. And I say, okay. I go here. I click the license file. I click OK. And it says your license has been accepted. And I say, thank you. I don't know why it's doing that to me every time. I'll probably try to reinstall it this weekend. It's just been one of those things that this semester jump every time it wants me to reinstall. So when you bring data into jump, you have to make sure when you paste it, if it has column names, you paste with column names. This did not paste at all. I actually just pasted the question. So this is completely wrong. Hit Control or Command N, which is just going to do File, New, Data Table. File, New, Data Table. Now, a lot of times, this is a common error right here. We're going to go to copy to clipboard, and then hit Control-C. So we're copying the data by going and clicking the data. Let me show it again. Going to right here, clicking this, and go to copy to clipboard. Make sure to hit Control-C right here or Command-C to copy it. Now, when you're inside of Jump over here, you want to paste. But if you paste and it looks like this, you're actually good. This is when we paste without column names. If there was a column name, which this time there's not, you want to go Edit, Paste with column names. Control V or Command V, just regular paste. Control Shift V, paste with column names. You can click the Edit, Paste with column names. But look right here, the first observation went in the column name. Well, if there was a column name, that would have been good, but there's not. So do I want to use option 1 or option 2? Option 1 was pasting without column names right here. Option 2 is pasting with column names. Which of these options do I want? Do I want to do option 1 or option 2? This is when I pasted without column names for this one, which there's not a column name. Or option 2, where I pasted with column names and it put the first observation as the column name. Or the first entry as the column name. So I want to do number 1. Great job, Kenneth, right there. And here's another issue that sometimes people have is a lot of times people, I've noticed it all the time. Someone opens this and then they automatically click inside of here and then they paste. That actually worked. But usually I tell people not to click inside of there. I say open it and now paste, but don't click inside of it because I've seen issues when people click inside of it. So if you just open and paste, you should be good right there. And then it should be blue. Blue means quantitative. Red means categorical. We don't want it to be categorical. So if you see red right here, it's not going to analyze properly. And you would go to analyze distribution. And I'm guessing you saw something like this right here, Kenneth, where it's just kind of flat because it looks uniform because there's only one duplicate observation right there. And that's that little peak right there for the duplicate observation. If this occurs, just redo the data. There is a way to fix it, but it's a lot longer. I would not suggest doing this method. It's more clicks than I usually want people to go through to go in there and go to the column info, but you can fix it that way too. And then it can't have any sort of categorical values in it. It can't have like the letter A in it. See, now it's going to change it, and that'll cause a problem right there. Awesome. Histogram looks great right now. That's what we'd like to see. So if you want, you can make a histogram of your data with Analyze Distribution. Analyze Distribution. Because remember, histograms are only for quantitative data. So it does say histogram if you make with the categorical, but it's a bar chart technically. It's a bar chart jump. So here we are with Analyze Distribution. And here is our histogram. You can also kind of deduce what this would look like. This is going to help us answer one of the upcoming questions, but it is a right-skewed data set. You notice the extreme high value over there on the far side of the data, and we can also kind of know this because 111 is a value that should be far away, and then the data should be clumped up here at the beginning. So let's go look at the data itself. 111 is kind of far away. Then the data is clumped up around 102. This is where the data is more spread out, which is going to identify for us that it would look something like this right here. This is what we drew inside a jump, so that's a huge help. Remember, it's just a far out data point over there on the right. It doesn't look exactly the same. We can probably get it to look better if we grab the change bin widths. And there we go. Look at that. Changing the bin widths, which is just the hand tool right there. So the hand tool allows you to change the bin widths. We've now created the exact same thing. You probably want to go over here and go to histogram options, count axis. And we preferably like to put, counts. Well, sure, why not? Histogram options and count axis. There we go. We can add the count axis and see pretty much identical to what they're showing right there. 10 observations, 11 observations in these bins, and we have the same data. Now, the first question asks you, the mean time was this with a standard deviation of this. If the normal model is appropriate, what percent of times will be greater than this? What is the first thing you would do with a observation? If you are given something like this on the test, you should take that observation and turn it into a what? What is the first thing you should do? I like David and Lane. That's a great answer right there, Kenneth. Excellent work. Let's throw out 1,000 points again. We're throwing out those big 1,000 points. I would go to David M. Lane. You can't do that on the test. And I would Z-score it. Blake, great answer there too. I would Z-score it. So Z-score is going to be observation minus mean over standard deviation. So we need to take the observation minus the mean over the standard deviation, which is 108.15 minus 103.90. I'm blocking it. I knew it. And now we divide by the standard deviation, which is 2.65. That is going to equal to a z-score. Tells us how many standard deviations it is above the mean, because this one's above. A z-score of 1.6. Now this means the area above is about 5.9%. Let's go look at that on the David M. Lane. So we're going to pull up the David M. Lane. I've been looking through the notes. Can you explain what's bad to cluster on minimum values because it's on minimum values? Well, we wouldn't cluster on minimum values. When you say cluster on minimum values, can you expand upon that? Is it a specific homework question? When you say cluster on minimum values, can you expand upon that? The percent of times that are greater than. So we go and put in our z-score here now, and we go above the z-score. And there's the value, and it's 5.4. I was kind of close with my guess. It's 5.4, so it would have been off. But Kenneth, we could have also, as you said, just put in the actual values right there. So let me instead show it this way and bring the David M. Lane over here. And we could put in the values for it. So we could put in the mean of 103.90, the standard deviation of 2.65, and say above 108.15, and we get the same value of 5.44. Important to know that the z-score does the same work for us as doing it with the context. Finding it both ways is important. What is the actual percent of times higher than 108.15? Well, let's go look at the data right here, and if we draw on it, there are 53 times, I think. So 108.15, right? I think that was right here. How many times are above that? How many times are above 108.15? How many times are above 108.15? How many times are above 108.15? How many? This is where 108.15 is at. How many times are above it? 5. How many times total are there? You got to look over there at the, you can't see it. How many times total are there? So there's how many times total are there? So there's the answer. 5 out of 53. We're just finding that there are 5 out of 53. So we can go and find the actual amount by going 5 out of 53, and that's the actual answer. We'll just copy paste in and delete the decimals down and go right there. And there's the answer to the actual. Are these two percentages close? Well, if someone tells you they're going to give you 5% of their gold or 9% of their gold, that's a pretty big difference. So the percentages should only agree. No. The data is, why would these two percentages not agree? The data right here is not unimodal and symmetric. Unimodal and symmetric is another name for the data looking what? Unimodal and symmetric is another name for the data looking what? So the data does not look this, as we confirmed down below. That's how the data actually looks. Normal, great job, Kenneth. So it would follow this if it was normal, but it doesn't. So that's bad right there. What can be seen from the histogram? Right skewed or left skewed? Once again, we love knowing this right here. Right to the high, left to the low, whatever way the Monster Man's tail goes. So what way is this skewed? Should be easy. Free points on the test if you ever get a question like this. What way is that skewed? Right to the high, left to the low. Whatever way the Monster Man's tail goes, what way is that skewed? It's definitely right skewed right there. Easier questions when we get those because we practice them all the time. The data is it's skewed to the right. We should be fine on this. Check answer 100%. Woo! We haven't missed a question in a long while. I've just jinxed us here, so we're in trouble. Javen, can you expand upon that question? I think we're gonna do. And does that make sense, Kenneth? Working through that right here. Really good question. Good practice. Tougher question. I think we're going till go a little bit longer. Got class at 12:55 Knoxville time. You're welcome, Kenneth. Thank you so much. A little bit tougher of a question. Amanda, Katie, Javen, which ones are you wondering about? Question number 7 says Chase. Stat tool and nostalgia to listen. Yeah. And it applies. 7, 8, 9. Here we'll start with 7. And then we'll do 8 and 9 next. So we'll start with 7, then 8, and then 9. And we'll throw in a 201 question. If a 201 person says, hey, do this, we'll do that. Okay. Getting the assignment up and going. So we should have time to do probably all those, Katie, I think. So let's go take a look right here. Someone said number 7. I can only do a certain amount of work on a lot of these. So a lot of times just commenting on it. Oh my gosh. Made a really good dinner last night. Like, made some taquitos or things like that. For chapter 5 quiz, could we look at the normal distribution question that asks for the cutoff values? Yeah, can you put the star of the question? Mostly conceptual. Nice. Shaq, put the star of the question, which one it is. I probably could find it, but drop the start of it, and then I'll do it. You got it, Shaq. Thank you so much, Shaq, for being here. Let's throw some points in the chat. So, number 7 right here. We'll do 7 and 8, and then we'll do 201. And you're welcome. 5903. Here we go. There's no extremely long, uninterrupted set of vertical lines, so there's no obvious natural structure to the clusters. Okay, so that's what it's talking about with the dendrogram. We got to go look at a dendrogram over here. Dendrograms show you when things merge together. Here's the dendrogram for a different thing. This looks to have a natural structure of 4 maybe. So when you do a dendrogram, you're looking for really good separation when you're merging the clusters. A dendrogram like this, it doesn't have, it's got structure around 4 clusters. What did I say? Oh, I did cut it at 6. No one complained in class. I cut right there and that's 6. No wonder. No wonder people were saying 6. Wow. Someone should have been like, Brian, you're wrong. Shoutouts to morning class. IQ test, you got it. Good to see her, Noah. This has a structure of 4. I see why people said 6, and I was wrong. That has a structure of about 4 or 2. You're looking for this uninterrupted section right here where you have like a structure of 4 where you'd cut across here, or 2. The section for 3 is basically impossible to see. Well, they were right. I was wrong. This would have either 2 or 4 because you're looking at where you would hit 2. You could cut at 2. You're looking for these uninterrupted portions, but you don't always get nice, beautiful stuff. You sometimes get stuff like this. So you're looking for a clean spot to cut where you'd say like, okay, this would cut at 4, maybe 3, maybe not 2. When this is the case, we left arrow. So now what you want to do is you want to cut the tree. Do I have a tree currently stored? And then look at the aggregate of it. Okay. So you want to cut your tree. I don't think I have the output. So you need to make a hierarchical clustering, H cluster. This is not the answer, obviously. And we need the distance matrix on it. There we go. Store it as output. I'm just creating something I can use. And then from here, you want to cut the tree. And you can cut the tree where the clusters are equal to something like 2 or 3. And you can cut this right here. So you could go to IDs 2 and do the following. So you can get your IDs right here, and these are the IDs for the cars. You then want to take those IDs and store them into your data frame, such as you would go like IDs 2 right here and store your IDs and run it. Then you want to run the aggregate function on your data by taking, now be careful, don't use the IDs. Does this make sense? Do we need to have 3 different cut tree functions? You probably would. Sounds accurate right there. Because you're going to cut the tree in different spots to create, you could call it K2, K3, K4, K5, or whatever. I like to call it IDs 2, IDs 3, IDs 4. But you notice right here, you would change what it is because I'm calling it IDs 2. So when you run this, this is actually set up to run for you right here with the function already there. So what this does, aggregate is an amazing function. I'll show you it with a different data frame. Aggregate takes all the Y variables of interest. If you use dot and then you do tilde, we can go right here and go gender on data equals survey 10, because you know survey 10 is awesome. And then fun equals mean. And we might have a bit of a problem. Let me try this. Just to show what the aggregate does. Oh, we don't have reg cost loaded up. And is going to get mad. Fun is missing. Oh, wait. Oh, FUN. Capital FUN. Tons of fun. Oh, it did find it. So what did I just find? It does. No, it stands for regression class. I thought you said regression class. Regression class stands for regression because it's 320 regression. But what did I just find right here? Like, what does this value represent? Yeah. What does that value represent right there? This is why aggregate is so powerful. Well, that is the mean. And this is not really, I mean, it is clusters, so to say, but this would be supervised learning because there are, like, there's groups already defined right here. This is not unsupervised because there are answers to this. The people have actual defined answers to the gender right here. So this is not unsupervised learning because gender has an answer. Because we can actually maximize, people are put into the correct clusters right here. We're not trying to predict the clusters or something, but we know the answers to gender right here. So then it's supervised because we know the answer. If we tried to do something like predictive modeling. Hey, Noah, so good to see you. Noah, we got to throw 1,000 plus for Noah appearing. Noah, thank you so much for being on the Discord. Stat Nation Legends were asked a question today, which maybe you're tagging on that. Happy Friday Eve. It's Haslam Friday. Haslam Friday. Haslam Friday. Got to get down on Haslam Friday. We should make a parody video of Friday. What if we could get what's Rebecca Black to appear and like be like, it's Friday, Haslam Friday. Someone's like, it's Thursday, and you're like, Haslam Friday. Like talk about like the 3-day weekend. Looking forward to the 3-day weekend. It's Friday, Haslam Friday. Brian, you're so cringe, Brian. Whatever, I'll be cringe if I want to be cringe. But we should totally do that. Maybe when I come back to UT, we'll like film it. I can't sing worth anything. I can play piano. I can't sing. So yeah, that'd be really fun. We should like, I don't know. See, like Rebecca Black is one of those people who's just crazy enough to make a cameo in our video. Like maybe if we say like, hey, we'll fly you to Knoxville. Just if you just make a cameo, you just like look over and you say, it's Thursday. You say Haslam Friday. Make Mubot sing it. Some auto-tune. Rebecca Black did. When do you come back? I'll be back next year. Chelsea and I are coming back next year. But that'd be a lot of fun. I feel like she's just crazy enough to make a cameo in our video to say like, hey, look, we'll fly you to Knoxville if you want to spend a weekend visiting Knoxville. You just do whatever you want. All we ask is you make like a 1-minute appearance. We probably just need like 5 or 6 takes of it where you just, you know, I'll be back. Just like, yeah, I don't know. I think about all these crazy ideas. You'd be shocked. You reach out. Like I've almost had some things going. I've had a few people I've reached out to who've almost done some stuff. So she maybe would. So she's pretty popular-ish. She's still got stuff going on. Like she's made a pretty big career for herself. Shouts to Rebecca Black. She's a pretty good singer. She's a pretty good singer and it's got a pretty big career and turned a lot of it into I think she's got a pretty big YouTube channel. Yeah, she's like, you got your S tier people, like your well, the problem is Cameo has terms of service. So I used to like using Cameo, but you gotta be careful because they'll hit you with a TOS or something, and I don't want to be hit with TOSs. So I don't I Cameo's like cool and stuff, but it's like you can't be like using it and stuff. It's like they'll be like, oh, I don't want you using it for that, and I don't want to mess with stuff with TOS. I'd prefer say like, hey, Rebecca Black, look, we'll fly it in Knoxville. You make a cameo in the video, and we make a Haslam Friday video. Like call it Haslam Friday. Next question. Looking at the centers for the 3 cluster team. 1 second. I am back. Okay, let's mark the question right here. We'll charter Spirit Airlines flight. Oh, I literally saw Spirit Airlines flight as I was leaving on my last flight when I came to Knoxville, and it was pretty hype. So here we are looking at the centers for the 3 cluster schemes. The only options for the clustering characteristics is baby. Cluster scheme has 3 values of 2.02. Why is 2.02 pretty odd? Bussin does allow delta. Why is 2.02 kind of odd? Two point oh two is kind of odd because it's outside of 2 standard deviations. Oh my gosh. So when we're doing this, we're actually using what's right here. Shoutouts to 201 again, because 2 is kind of odd because these values you're looking at are what's. These values you're looking at are what's. These values you're looking at what? Hyper Pop Queen, is that one of her things? These values you're looking at are what's when you're looking at the clusters before we turn them back to the original values. I mean, kind of outliers, but looking at this curve right here, everything on this curve is what's. Everything on this curve is what's. This is the normal curve, all z-scores, right? So when you're looking right here, good job, Kyle, right there, that's what we're doing right here. 2.02 is kind of unusual. It's a little bit of an outlier, right? So we want to talk about the distinct characteristics of the groups, split into 2. Oh, this is which of the groups has been split. Oh my gosh. My body is just like, get some more coffee here soon. Okay. So right here, the question is, because the question asks, look at the centers for the 4 cluster schemes. Which of the clusters 1, 2, or 3 has been split into 2? And comment on whether your understanding of the households increases when going from 3 to 4 clusters. So we need to look at comparison metrics between the clusters. Does that make sense? So we need to look at the 3 cluster scheme and the 4 cluster scheme. Now, this is not a 3 cluster scheme, but a 3 cluster scheme is going to show you the 3 clusters. Does that make sense what the 3 cluster scheme would show you? Which one is split into 2? So to know which one is split into 2, you can kind of look at the dendrogram over here. Looking at the dendrogram, you can see right here that when we're at the 2 cluster scheme right here, doesn't make sense, and I'll show you how to find the answer to this. But on the 2 cluster scheme right here, you have cluster 1 basically and cluster 2. Now the numbers, be careful, they might change, but this is going to split. Doesn't make sense, just visually speaking, that this one splits. Well, we're not going to use the dendrogram quite because it won't tell us the exact answer, but does that make sense how that is splitting right there, that splits? So that's where the split's going to happen. That one's going to split apart. Now, to find that answer, we need to have our 3 cluster IDs stored. And so let's go here to cluster IDs 3. And now we've cut with cluster IDs 3, and then we need to store the cluster IDs 3 into cluster IDs 3 right here, and we could actually go look at it. So if you have the cluster IDs stored on your data frame, you can go over here to your IDs, and this is with the 2. Now, if you look, which of these stayed the original cluster numbers? Which cluster originally, which of them got split apart? Does that make sense? Now, you see how there's clustered with 2 clusters, 1 and 2. So which of these clusters got split apart when you went to 3 clusters? Which of them got split apart? Remember, the numbers don't matter so much. Which of these clusters got split apart? Do you see it? Which of these clusters going from 2 to 3, which of them got split apart? The cluster that got split apart was cluster number what? So for example, Valiant or Duster. Well, which of these got split apart? Cluster 1 got split apart or cluster 2 got split apart? Which of these clusters got split apart? Would it be cluster 1 got split apart or cluster 2 got split apart? And now explain how we know this. Did cluster 1 get split apart? Cluster 2 got reassigned to be cluster 3. So this is actually cluster 2 right here. Like, this is cluster 2. The numbers, remember?
It doesn't matter.
This is cluster 2, and then it was called cluster 3 afterwards. Well, do you see this is still the same data? Do you see how these rows right here, all these rows are still one cluster? Like, this is cluster 2. Like, the cluster IDs that I stored, this says this is cluster 2. Like, all of these points right here are in cluster 2. Now, they're called cluster 3 over here, but they're all still the... And then look at cluster 1. Cluster 1 got... So this was cluster 1 up here, which is a ton of the data, but then cluster 1 got split apart into cluster 1, 2. So this is like cluster... I don't know which of it is technically, but one of these is now cluster 1. One of these is now cluster 2. Cluster 1 got split into 1 and 2. Exactly. And that's what is happening right here where it's split apart. So it was cluster 1 originally. This is when it's cluster 1 originally. And this is when it's cluster 1 and 2. This right here is when it's originally cluster 2. And then this is when it's reassigned to cluster 3 right here. So if we draw it out here visually, it would look the following probably. I can't confirm the last few numbers. This is when this is cluster 2 here. But after this point, it's called cluster 3. This is when it's called cluster 1, but then it gets cluster 1, cluster 2. Because if you cut right here, there's 3 clusters, but those are the cluster IDs. Does that help make sense of it right there, Katie, to show that, to show the assignment? I hope that kind of visually explains it. Because after the cut happens, the numbers have changed to where now cluster 2 becomes numbered as cluster 3. And cluster 1 gets split apart into cluster 1 and 2. And that's where it's happening right there at a height of 5.5 or so. Oh my gosh. So much craziness. Fall has begun. So with that, I think we're going to do a 201 question. We'll look at 9 real briefly. What does 9 ask? And then make sure to comment any sort of significance. Kroger finds 5 clusters seem to be the most useful. Is it talk about the characteristics? Is it? Oh, look at the medians. So you want to use the aggregate on the medians on the original data, I believe, round to the nearest dollar. So you want to go back up and grab your aggregate function. Aggregate is just super powerful. So what does it mean to characterize the new clusters that emerged? So to characterize them means to kind of talk about the characteristics of them. So look at the z-scores for number 9, add the cluster identities. That's where we're adding the cluster identities right here to then sort. Like we can do things like aggregate, the MT cars data set based on, we don't want to do that. We want to do dot tilde IDs 3 of the MT cars data. And then we want to go right here and go, not data, we want to go to fun equals median or something like that. And there's the median value of all the clusters. And then we'd want to talk about these things right here. Rock is going crazy. I've been looking for the exam review, but I can't find it. Does anyone know where it is at? Review 1. There you go right there. Review in the chat right there. Mubot knows where those reviews are at. Good stuff right there. Was there a 201 question, I think? I thought there was a 201 one. Oh, the IQs. Thank you, Shaq. Some IQ tests are standardized. So some IQ tests. Let's go do that, and we'll end with that one. Good questions today, everybody. Lots of 474. Lots of 474. Lots of good tips and helps. Thank you, Katie, right there. Stat 201, Chapter 5, Quiz 2. Some IQ tests. Okay, you're welcome, Shaq. Thank you so much. And a lot of these questions are very similar. So let me put that at the start of this because someone might be watching it later and be like, how do I do this? Some IQ tests. Here we go. Let's do it. So if you're watching this right now in the future and you're working on this assignment, A lot of these questions are very, very similar. Like if you go to these over here, it's asking for percentiles. So a lot of these questions are very, very similar with percentiles. So this question should be a big help for anything that asks you to find percentiles on the curve. I'm going to do this solving it by talking through the theory and how it would apply to tests. And then I'm going to tell you how to solve it. So when you get this question right here, it re-randomized. I had such a good version earlier. When you get this right here, we want the highest... Oh, wait. We want the IQ one. Here we go. So this question right here is asking about percentiles on the curve, and we're looking at the highest 15%. The highest 15% is known as the what percentile? The highest 15% is known as the what percentile? You need to know things like this very quickly. Just like with practice, if I said the highest 15% is known as the what percentile? So if we had the highest 15%, percentile means area below the curve. So the highest 15% is known as the what percentile? The highest 15% is known as the what percentile? These are things you have to understand, especially for the test. If something says percentile, we would need to know the highest 15% would be found at the what percentile? The 85th, great job, Amanda, right there. Yep. So the 85th percentile is where it's at because that's the area below the point. The lowest 35% is going to be down here. So we'd have a drawing over here and have the lowest 35%, so 35%. We're just kind of doing little sketches to understand what we would need to look at. The middle 80% is going to be somewhere between the middle 68 and 95. So if you were to draw a curve for the last question, you would have something like 68% is within here, 95% is within here. Remember your standard deviations on -2 and +2, -1 and +1, 68%, 95%. So the middle 80% would be somewhere in here and somewhere right there. So that's about the middle 80% is our answer because we want somewhere between 68 and 95. Now, what if I told you I could get pretty much all these questions without using the David M. Lane? I'm only really worried about one of them. I should get at least one of them. So this is a portion where you're not meant to do the work I'm doing right here. You're meant to understand and be able to do the drawings. And a lot of times we'll have questions where we show you pictures of the applets. So using my knowledge of the David M. Lane, or using my knowledge of doing this, the highest 16% is a little bit more than one standard deviation above. So it's probably going to be out this. That's close to the answer. The 35% is super duper hard to guess. So that's going to be a little bit less than one standard deviation. So that's going to be, it falls off pretty quickly right there. So that's going to be about 96.2. That's a very hard number to guess. 80%, I know this because I know the z-score for an 80% conf roll is 1.2816 by doing a lot of these problems. So it's actually going to be plus or minus this. So it's 115.4. And also it is going to be 100 minus this. And I only know this because I've worked these problems. I'd love that, Shaq. I can take some guesses. I got 50%. I only got the last one correct. The other one, so I got half of it correct. This one, it's probably, we're getting close to the answer. These other ones are close. The other two are really hard to guess, but we should be kind of close. And that's using my knowledge. I just know the z-score for the last one because, and let's show how to get these answers now. So if you're working the problems, I want you to do drawings and understand like we did when we were thinking about what it should look like for the answers right here. Now we're going to go over to the David M. Lane and show how to get the answers for this problem exactly. When you go to the David M. Lane, you need to put in your mean and your standard deviation for both areas on the curve, or both buttons. So I put in for both because some questions have you use both, some have you use one. Just put it in both to make sure you've changed your numbers. We're going to be using this one right here, which allows us to talk about the percentile. To talk about percentiles, we talk about the area below. So remember how we were just doing our drawings a moment ago? Well, when we're looking for the 85th percentile, which is the top 85%, we should see a drawing that looks something like, let's draw it out again. Here's our curve, and the top 15% is going to be over here. So that means we would be shading the area below for doing it as a percentile, and we should see something like this. Let's see when we type in 85, if we get a drawing that looks something like that, and take a look. Our little sketch, does that look like it, Shaq? Does that kind of look like the answer? Oh, I should have guessed right at 112 because that's where the top 16% is. I knew that, but I was going way too high. So if you look at this, our drawing looks a lot like it. Exactly. And remember, percent means area below. Nate said, well, Brian, it said, so it's 112.4, kind of close. I wish it was closer, kind of close. So that should be another correct answer, and we're just one answer away from getting this correct. The top 15%, remember, this is highlighting the top 15% for us right here. That's the top 15%, but that's also the 85th percentile right there. So make sure you understand that percentile means area below the curve, so the top 15% is the 85th percentile. The next one says the lowest 35%. Well, that's the 35th percentile. So once again, we're going to do a quick drawing right here. And so if we do a quick drawing of what the curve should look like, theoretically, we would have our curve right here. And then if you go down one standard deviation, this is going to be the bottom 16%. The middle or the bottom 50% is right here because the middle of the curve is 50%. And this is the bottom 16% because inside of one standard deviation is 68%. Outside total is 32. Half of 32 is 16 using the empirical rule. So our drawing should theoretically have a line somewhere inside of here, and then we should be shading. So it should be somewhere between right about here and shade downwards. So the bottom 35, I put my mark right about there. Oh, I was a little bit over. So there it is, and here's our quick sketch of what it should look like. And if you notice where we are from the top of the curve over, it kind of looks like it. So we know what we're looking for. These are the things we can solve without the applet. We need to know what the applet's showing us and be able to interpret to say, that's the bottom 35% shaded in. We could also change the way this looks on the test to show you the bottom 35 by doing something like this right here, because if 65% is shown as the top, then 35% is the bottom. So sometimes the test will try to show you a different graphic, and then you have to understand if 65% is shaded, then that's where the bottom 35% is. It's right where that line is right there. You can also confirm because it's a lower number, 95.4. How close were we? 90. Oh, we were close again, but not close enough. That's a tough one to guess. And that should get all the right answers. Now, the last one we had right here was the middle 80%. And we already did the drawing for that one. So let's just show it right here. If we go here to between and we do 80%, and that gets you the answers right like that. Now, if you notice, I solved this one out very quickly and exactly. That's because later in the class, we will be doing what are called confidence intervals, and we will use z-scores for them often. The z-score for an 80% confidence interval is 1.2816. It'll round it to 2, but there it is, 1.282. And if you rewind the video, you'll notice I use that number because I've done this a bunch of times and I know the z-score. So since I knew the z-score, I was then able to take the z-score of 1.282. Here's 1.282 times that by the standard deviation of 12, and that tells me the answer is that far above the mean. And I think they're actually carrying the decimals, 1.2816 times 12, and there it is right there. Or maybe they're not. I don't know what they're doing. But does that make sense, Shaq? So there's the answers to the last one, the middle 80%. Once again, do the drawings to help yourself out, and then understand that they could have used z-scores right here also. So if you have the z-scores, you could also find the answers. So a lot of times people say, well, what if they show us the z-scores? Got 100, Shaq. That's worth 1,000 points. Great work, Shaq. A lot of people are working on this today. This is a tougher quiz, and then the more you can do the drawings, the more you can understand what it's showing you, the better you are on the test. These are some of the toughest questions. And chapter 5, I'm just like, no, I want to send an email and be like, hey, everyone, chapter 5, you don't want to wait till like it's due an hour before it's due. You don't want to wait an hour before it's due. It's a tougher chapter. Shaq, just huge shout outs to you right there. A lot of the questions are very similar in how you work them. As soon as you know, we never did this one. What does it show? It shows you the histogram. That's pretty normal. Pretty normal. And then they're showing you the spots, are they? So between those values, that's really tight. So just once you get the standard deviation. So I think it wants you to find the standard deviation for this, I bet. Because I was looking at those numbers. So that's 4 standard deviations. 0.0475. According to the normal, what percent of you expect to earn more than 2 standard deviations above the mean? So it's doing outside of 95. Hard time, whichever 6 I know. Probably spent a lot of time on 6. Is that percent appropriate for these data? Yeah, because it's pretty unimodal and symmetric. Yeah, you want it to be unimodal and symmetric. Now let's draw the 30 CEOs from the logged data. We drew 1,000 samples, found their mean. The distribution of the means is given above with a standard deviation of 0.05. Do you think this is going to... Wait, here's the initial. There's a little bit of an... I think I'd get mad about that outlier right there. Are they seriously... I think I say that's skewed. Let me look at the original again. They're going to say that's skewed, isn't it? No, it's the log of it. Do I not have the original? The glass... Yeah, I think the original is going to be skewed. Why do they not show... To view the initial histogram. This has got an error. Initial histogram of log compensation. The Glassdoor in millions of dollars for CEOs of large companies. Suppose we take the logarithmic of the CEO's compensation. This term of the log is given below with a mean of this and standard deviation of this. So that is the logged. Is that percent appropriate for these data? No, because they is skewed. They're saying it's skewed originally. Now let's draw. They need to show the initial. I think they have an error right here. That's at 1.1. That looks not. Isn't there? Are they saying it is appropriate? Wait. Never second guess yourself. Never second. So they are saying that is the initial. They wrote log CEO compensation on the bottom. And then they say initial. But you've logged it. And then you logged it again. Yeah, that's I'm glad we did this one as a quick addendum right here, because that's really confusing that they say it's the initial and then they log it. Because what we're talking about, and this is so interesting because Amanda, right? 474, we're doing this exact same stuff right here when we take the original Kroger data. And you'll notice right here with the Kroger data, load up all our data, we're doing the same sort of stuff with like alcohol sales is going to be shaped like this. And can we use the normal model on this? The answer is no. But could we use, and this is what they're getting at, could we use the normal model on this? Now, we also want to add in the plus 0.01 for our data. It's going to give that second peak, and you wouldn't want to use the normal on this. You could use the normal on this. You wouldn't use the normal on this. You could use the normal on this. You wouldn't use the normal on this. Normal is unimodal and symmetric, not right skewed, or not bimodal. So that's what they're getting at right there with this question. So it's just important to understand the theory of what they're getting at. I really think that they didn't mean to put log on the bottom of that, because the initial would be the unlogged values. This is no longer the initial data. It's the log 10 of the values with a 0.01 added to it. The negative infinities were removed right here because when you log 10, 0, you get negative infinity. This is the original data right here, which we should not, which is what they thought they were going towards. But they are just talking about that graphic in A. So that's just a little hint right there for those. Well, we have class here in 10 minutes for some 474. Until then, bye for now, everyone. Bye!